Hey guys, welcome. Hope you're having a lovely day, and let's get started with Chapter 3. In Chapter 2, we started to talk about variables. We identified what a frequency table is, a data table as well we talked about. We talked about, let's see, what else was big? Well, those were the biggies. Oh yeah, context. Context was big in 2. All right, so in Chapter 3, we're really excluding our view to ways to represent or display categorical variables in data that is categorical then. And also we're going to start to talk about independence. And independence is a topic that starts off important, it finishes important. Independence is huge to statistics. When we get to some statistical analyses that we'll get into second semester, whether or not we have independent variables, which will make more sense as we go through the slides, really determines whether or not we can use those processes that we'll see in semester 2. So, okay, kind of already said the first sentence here. We're going to keep the current color scheme. Second sentence, recall that frequency tables allow us to see how all of the data we're looking at falls into possible values our data can take on. So we have 2 frequency tables here. And notice as we go through this, to the best of my ability, I may have made a mistake and not done this on a few slides, but for every graphic that you're going to see today, or table like we see here, you're going to see a title for that. That's important. It's important in any test or quiz you take, and it's important, very important on the AP exam as well. So don't do something like this. Don't omit that title. Make sure that you've got an appropriate title for the table or display that you're making. Now, what an appropriate title looks like may seem kind of arbitrary at first, but as you get practice in this class naming your displays, it'll be easy as time goes on. All right, so we've got 2 frequency tables here. Our data is, well, for the first one, it's not truly a score is not truly a categorical variable over here. But that doesn't change the fact that a frequency table is still often used to display categorical data like we have here for method of traveling. So some group of people were interviewed, looks like kids, and the method of traveling that they used was identified. We consolidated all that information from the respondents or the subjects into just the data values that method of traveling is taking on. These rows here, the first column has each of those rows in the first column. Those are the data values that the variable method of traveling is taking on. So we've talked about a frequency table before. Those stick around. Sometimes, I won't say sometimes, I think most of the time, a more useful frequency table than just showing the frequency or the counts, like you're seeing in the second column, all through here, more useful than that is a relative frequency table, which performs similarly, but when we say relative frequency in this class, we're talking about the percent of the time that occurs. So if you check out this first frequency table with me, talking about previous operating system ownership for computer buyers, we've got this categorical variable, previous ownership, and the data values it can take on are, some people did not previously have a computer, so they reported none, no previous operating system. We've got Windows, we've got Mac, and we've got a final row for the total. Well, the relative frequencies allow us to know, rather than just the counts that we got from people who fell into the none, Windows, or Macintosh data values, instead we know how they stack up relative to each other as percentages here. That tends to be an easier way to understand how the data values relate to each other. So in the second column, it's a little bit harder. I mean, you guys are capable, you're very good math students. It's a little harder to see that previous ownership occurred about a fourth as often as a Macintosh ownership, versus in the relative frequency column in the third, you can much more easily see that 0.17 is just under a quarter of 0.71. The numbers are smaller, they're easier to see and process. You got another relative frequency table to the right of that for reading scores for a first grade class. Here, the variable in the first column, note again, I guess I'm kind of going back and forth here. The reading score, that's quantitative. That's probably measuring, I mean, we can't know for sure that that is used quantitatively to measure the quantity of something, but it probably intuitively should mean number of points scored on some sort of assessment. So you've got in the second column, you've got the frequency like we've seen in the past, and then the percent in the third column, which allows us to know how these different data values in the first column compare to each other. A more intuitive and easier way to process the data. So percentages are awesome in frequency tables. And when you use percentages in frequency tables, you were talking about a relative frequency table again. All right. So last slide, we had a description of the data, but we didn't have any way to visualize the data as well. Well, one of the best tools you've got, and probably I think it's the easiest tool to design for qualitative data, is a bar chart. You've got, let's check out what this bar chart's all about. This bar chart is average square footage by style for a variety of different homes. Okay, so on the bottom axis, the horizontal axis, we're told that the variable is style of homes, and the data values that this variable style of home can take on are condo, ranch style home, which I think is one story. It tends to be kind of flat and spread out. Split, which is kind of I think it's a split between a 1-story and a 2-story, and then a true 2-story home. So we've got the data values that our variable style of home can take on, and then the vertical axis, square footage, is the average amount of square feet per data value we're taking on here. In a sense, it's your count. The vertical axis is a little bit like your count because the way that they arrived at the square footage for each of the data values, condo, ranch, split, and 2-story, all they would have done, so they would have interviewed people who had these 4 different types of home. They would have asked them about their square footage, and then they would have added all of the condo owners' square footage up, divided through by the number of condo owners. So that's going to give you the square footage for condo. So this bar chart is a little bit funky, and it is really tough to find great bar charts to present to you guys in Google Images. But what you can tell here is that it's showing relative to the count for each of these data values, a tall or a short bar. So clearly here, the condo owners tended to have the biggest square footage in their homes, while the ranch-style homeowners tended to have the least square footage on average. Okay, and the nice thing about this, as opposed to a relative frequency table or a frequency table, is again that human beings are so visual, and actually increasingly so. I heard a little bit of a tangent here, but I think it was like in the 60s. The majority of people learned best verbally, but because now with the advent of the computer and displays all over the place, the majority of people are actually visual learners, and hence in statistics you're going to see a lot of visuals and you'll make a lot yourself. All right, so there it is. A bar chart is in essence a frequency table. All right, you've got a second one here, and I like this bar chart a little bit more because notice while it too is titled, you've got measles by month in New York City from that date range 1931 to 1971 versus average square footage by style here. The vertical axis in this first example I showed you was not the counts for the data values that I've highlighted in red below, condo, ranch, split, and 2-story. While in this bar chart you do indeed have the counts, or cases as they're called, in the thousands on the vertical axis. So that makes it more like a frequency table, which remember counts up how often you have these data values, data falling in these data values. So what are we looking at here? Got measles by month in New York City from 31 to 71, and we've got the months listed below. And we would not say that this is a relative frequency bar chart, because the cases are what are represented on the vertical axis, not the percentage of all cases. We don't have, say, the percent of all measles cases in January in New York City during that range expressed as a percentage. We know that according to the height of that bar, we're looking at almost 40,000 cases of measles during January in that 40-year window. Okay, now there's the last sentence here says something that's important. There's a reason we space between the bars in a bar chart. In general, on this slide, there is significance to the ordering of these letters right here, okay? Clearly those stand for the first letter of the months of the year. So you've got January, February, et cetera, on through December. But if you look at just this last slide right here, with those data values, condo, ranch, split, and two-story that I've highlighted in red there for you, the gap between the bars is supposed to signify that it doesn't matter where these data values fall. For instance, condo could have been the first bar that we represented, but because these are qualitative data values, they're not numerical, the ordering from left to right doesn't really matter. We could have had split first. We could have had ranch first as the first bar represented. That's why we put a gap between these bars in a bar chart. When we get to histograms that deal with quantitative data, you won't see gaps. So actually, again, getting back to the importance of visuals, as we tend to be visual in this day and age, when you see gaps between bars, if it's a well-designed graph, you should be clued into the fact that you're talking about qualitative data right then. Without gaps, you've got quantitative data. So again, the ordering of these bars is arbitrary in general, as you can see, because here, again with the months, there is significance to the ordering of those letters. All right, so often, or not often, really similar to a bar chart is a pie chart. It functions almost the exact same way. Instead of the counts, pie charts are really awesome at displaying the frequencies, the percentages, right? So check out this first pie chart. You've got birthday wishes by channel, and then you've got a color coding set up for the different slices of the pie. You've got 6 slices. Those are so it looks like, I'm doing an inference here. It looks like someone took all the different ways that people wished other people a happy birthday throughout some period of time, counted those different ways up, and then the percent of the pie corresponds to how often that method of communication was used. So email and, no, that's not Facebook. Twitter. Email and Twitter at the time that this was made were not used often. Now, I bet that's changed. It's probably a little bit old. Email and Twitter were not used often. Facebook was used like crazy, et cetera, et cetera. So the pie chart's nice when you want to be able to see how the counts of these data values, of email, of Skype, of phone, SMS, I don't know what that stands for, Facebook and Twitter compare to each other. So a pie chart is a little bit like I'm not going to find one here. It's a little bit like a relative frequency bar chart, and that, again, you can know how the data values compare. Let's see, was there something else I wanted to say on this real quick? Oh yeah, there is something else I want to say on this with the pie chart. Not that this problem is exclusive to a pie chart, but so far in all the graphs that I've shown you guys, there has not been any overlap in the data values, at least that I know of. However, as I'm sure you guys could find here, let's establish a context, and let's say a researcher goes to high school students and learns about just of the high school students who are substance abuse users, what sort of substance abuse they are engaged in. So let's create a hypothetical pie chart here. Let's create a big slice of the pie that represents drinking. Let's create another slice that represents pot use. And then this last slice of the pie will represent heavy drinking here, okay? And let's give this a title of Teen Substance Abuse by percentage, but I'm going to omit the percentages from being in those slices of the pie. I don't really think they're essential. Let's just leave it at teenage substance abuse by category. All right. Now, as I'm sure a lot of you guys have already seen, you've got a problem here where we're not being honest with our display of the data in that heavy drinking and drinking clearly overlap. Anyone who's engaged in heavy drinking is technically also engaged in drinking. So you've got an overlap of the categories. This would not be, it sounds like the way the data was collected was probably done poorly if you ask people if they engaged in one of these three things and required one of these three specific responses. But bottom line, we can't make a display of the data when you've got overlapping categories. So pay attention to that, be careful. I'll let you know right now that you're not frequently going to see cases where you've got overlapping data values like this, whereas like you do with heavy drinking and drinking. But it does happen sometimes. And just pay attention to what you're keeping track of. Again, context is important, and you've got to follow the context as you look at the data. All right, next one, also big, also a mistake that can happen. It doesn't happen a lot. It happens more as we start to create graphs than when we're experienced with creation of graphs, of data. We want to make sure we don't violate the area principle, and you've got two violations here of the area principle. So in the first display, which is not really anything we've seen in the notes today, it's a little bit like a bar chart, I guess. You've got the shrinking family doctor in California, percentage of doctors devoted solely to family practice, tracked from 64 to 90. And we are told on that top horizontal axis that in 1964, 27% of doctors were devoted solely to family practice, whereas in 1990, only 12% of doctors were devoted solely to family practice. So there's a big drop there, but that big drop from 64 to 90 is made visually even more significant by the fact that you've got this first doctor is about, let me extend the page here real quick, he's about 2 times as wide as this guy is, in addition to being about 2 times as tall, right, as this guy over here. So the area principle is being violated because we have the percent of doctors in 64 looks to be much greater than it is, because knowing that the area formula for a rectangle is A equals L times W, well, you've got an area that's about 4 times as big over here as you do over here, right? So your eyes, again, don't fool the eyes when you make these graphs and when you make these displays. Be careful that if you want to express that, and I'm rounding here, that 27% is about twice as much as 12%, a correct way to do that would be to, if you wanted to make bars to do that, to make 2 bars that have the same width, one being about twice as tall as the other, okay? And then it's not confusing to the eyes. Second case here, you've got another violation of the area principle because man, I can't see that on the smartboard. The 30%, the green slice of the pie that's 30%, is closest to your eyes, hence it appears to be much bigger than the 10% slice that is blue in back, even though the blue slice should be, of course, just a third, or right at a third, of the area of the green. So be careful. Yeah, be careful when you make your displays. Make sure that you're not confusing the eyes. You want to be honest with the numbers, and you want to be honest with the areas. All right. So far we've talked about different ways to display, i.e. pie charts and bar charts, and describe, i.e. frequency tables and relative frequency tables, qualitative data, but we've only done that in a single variable. A contingency table is a description of how data values fall for two variables. So I like this contingency table. It's got a lot going on, but I think it's also kind of cool. So I'm going to make up a context for this. I did not... Oh, okay, the title. I think the title is appropriate to understand the context. So we've got preferred fish variety for respondents in European countries. So Spain, France, Italy, and Greece, we went to those 4 places and interviewed 1,846, 1,447, 452, and 1,556 people per country, respectively, across the board. And we found out from those groups of people which of these 8 categories in the left column of fish they prefer to eat. All right? So 2 variables are being tracked. You have country of citizenship, and I'll just put citizenship, and then you've got preferred fish. All right, so each of these cells, and I'll highlight a few in blue, are counts according to the data values of 2 variables. For the first one I circled, that 293, you've obviously got a number of people who like grouper fish and who are from France, et cetera, et cetera. So that's useful because it's good to understand how things fall according to 2 characteristics for people, respondents or subjects, or things, experimental units. One other thing I want to bring your attention to that's big is that, let me erase the blue things here, and let's do this in green. You have what's called a marginal distribution right here. Now, what is a marginal distribution? Well, it's in the margins, it's in the side at the bottom here of the contingency table, but a marginal distribution shows the breakdown of the variable country of citizenship without any regard for preferred fish. So really, what I just circled in green, that is enough to make a frequency table for the variable country of citizenship. So with a contingency table, everything that's kind of in the middle, all the data values that correspond, all the data that correspond to 2 data values like bass in Spain, like France and swordfish, et cetera, that's information from 2 variables, while the first circled 4 numbers is the marginal distribution of the variable country of citizenship, while the second set of 8 circled numbers would be the marginal distribution for the variable preferred fish. And there too, you could make a frequency table of that. Now, is that necessary? No, because that information is already in the table. But those margins give you the counts with regard to just one set of data values instead of all sets of data values from both variables. All right. Okay, next slide. We're going to talk a little bit about independence here. So the way, before we jump into this, I think the best way to understand independence is to think about independence being that one variable is not affecting another variable, okay? Whereas dependence would mean that there does seem to be some sort of link between the variables. So we want to find out here, real quick, whether or not the country of citizenship and the preferred fish for people of those countries are independent or dependent. Now, to do that, we are going to show the conditional distributions of the fish type conditional upon country of citizenship. So what does that mean? So you've got, and I showed the 8 groupings of preferred fish type 4 times here, just so it's easier to process. So you've got, let me circle this first thing. This is one conditional distribution. This is another conditional distribution, third and fourth, okay? All of those are conditional distributions for the variable preferred fish. That is the variable we're keeping track of here. But they're conditional upon one of four different things. Citizenship from Spain in the first case, from France, from Italy, or from Greece in the second, third, and fourth cases. So what we're looking for, we've broken, instead of, in some sense, you can think of a conditional distribution as basically being the first circled conditional distribution there. You could kind of think as just being this, but instead of displaying the counts through here, we've expressed the counts as percentages, as you can see there, the 0.332, the 0.258, the 0.037, etc., etc. So we know of the people in that first circled red circle thing here, of the people from Spain, what percent of those people prefer swordfish compared to everyone else interviewed? What percent of people prefer sole compared to everyone else interviewed? Now, if the variables, country of citizenship, and preferred fish are independent, then what will be true is that you will see approximate, not exactly the same numbers, but approximate agreement for all of these data values, etc., etc. I'm not circling the only ones we look at. We would look at each one of these rows, the row of blue numbers, the row of green numbers, the grouper fish numbers between them, and we would see, okay, when I go from people interviewed in Spain to people interviewed in France, did the percentage of people who like swordfish change when I went to that new country? And yeah, clearly it did. 0.332 compared to 0.381. Almost 5% more people preferred swordfish in France than they did in Spain. And then when you jump to Italy, you see another increase. Almost 40%, over 40% of the people in Italy prefer swordfish compared to just 33% or just over 33% in Spain. So what does that mean? Well, it looks like the variables country of citizenship in the very top row here of our contingency table and preferred fish type in the very first column, it looks like they are not independent. Again, that means that the data values of one variable seem to affect the data values of the other. So where we live seems to affect what, or at least seems to be related to what type of fish that we eat. Now we don't know why that is. We could know, or it could be possible that people prefer these fish types because of some sort of cultural norm. It could be maybe because of availability. Maybe swordfish in Greece are less robust and taste worse than they do in Italy. Who knows? We don't know why the difference is there. We just know that it's there. So we cannot say country of citizenship and preferred fish are independent. We would say these variables are dependent. Okay. All right, moving forward, that's a big idea, independence. We'll see plenty of that. And if you have questions in class, please ask me. I want to nail those as quick as we can. Contingency tables give us the distribution of our data for two variables, but unfortunately bar graphs and pie charts only display a sample's distribution of data for a single variable. So what we've got here is a segmented bar chart, which is to the contingency table as a bar chart is to a frequency table. That is to say, a segmented bar chart literally shows, it displays the data according to two variables, whereas just like the contingency table does, whereas the bar chart, just like the frequency table, shows the data according to a single variable. So you got two data values tracked here. You got sales by region, I assume, for some company in the 2005 fiscal quarters, which I don't think, again, I told you guys I'm not much of a finance guy. I don't think that's January through March, and April through June. I think fiscal year like stops in March or something like that, but whatever. At any rate, you've got quarters of the year that are being tracked for this company, and the sales in millions of dollars. And the segmented bar chart not only has, in this case, 4 different bars for the 4 different data values of the quarters of the year, but also within those bars it breaks it up according to, what did I say sales was the other variable? The other variable here would be region of the country where these sales are occurring. So it just breaks it up so that within each bar, you know that it's the distribution of sales by region for quarter 1 versus quarter 2 versus quarter 3 versus quarter 4. Segmented bar charts don't, occur. They don't come up a whole lot in this class. So I don't want to pay them too much attention. Let's hit the next thing here. All right, example 1. Students in an intro stats course were asked to describe their politics as liberal, moderate, or conservative. Results are in the contingency table below. Now, why is this a contingency table? Well, it's tracking 2 variables, political views and sex for these students. And notice again, you've got 2 marginal distributions. You've got the marginal distribution of the variable political views on the bottom row. You've got the marginal distribution of the variable sex in the last column, okay, with the total number of students interviewed there at the very end. All right, so let's see what we can do. We want to produce a pie chart of the marginal distribution of politics in the class. Well, marginal distribution of politics is going to be the totals in the bottom row. That's how many people, the total number of people who are liberal, moderate, or conservative. Well, to make this pie chart, remember that there are 360 degrees in a circle. So basically all we need to do is know, okay, for the first slice of 85 liberals, what percent of 360 degrees should that first slice be? So we're going to say, okay, we know there are 192 people in all. 85 are in this first data value. That comes out to be, actually I didn't write that down. That fraction times 360 degrees. So you've got the first fraction is the percent of 360 that this slice will be. Multiply that by 360, and that's approximately 159 degrees that we will devote to the first slice of the pie. So let me insert here real quick my protractor. I'll center that, shrink it down so I can, there we go, shrink, oh, nope. Where is, well, okay, we can do it this way. 159 degrees, starting on the left in the outer scale going out, will be right about there. So, okay, we're going to kind of roughen it here. That's okay. We're going to like right there. Geez, that doesn't look right, but okay, whatever. We've got liberals here occupying 159 degrees of the pie. Okay. Next up, let's do the next one in blue. So these will be the moderates. 80 over 192 times our 360 degrees comes out to be exactly 150. So I'll take this guy and spin it around. So we're going to measure 0 on the left there and go out to the 30 right there. Okay, let's move this away for now. And going out to that blue piece, we've got that was the moderates, and then last of all, that leaves the conservatives. Okay, and there you go. There you have made a pie chart from a protractor and the marginal distribution of a contingency table. Pie charts, you're welcome to use them. I think they're great displays. I think bar charts are more common, but it's good to practice doing both. When you make, hopefully you got this, or at least a piece of this from when I was talking about the area principle. When you make a display in this class make sure that you're trying to be as accurate as you can. Again, it really does matter on the AP exam. Okay, example 2, students in an intro stats course were asked to describe their politics as liberal, moderate, or conservative. So same data value, I'm going to produce a bar graph of the conditional distribution of politics among the females. Okay, so where's the conditional distribution of politics? That is the variable right here among just the females. Well, that's going to be all of these data values right here. And because they want a bar graph, we don't have to turn these into percentages. So we can say, well, okay, 35 is the biggest, 36 is the biggest count among those 3 different data values for political views. So let's take out a ruler really quick. Insert a ruler. Let's measure this guy real quick. Let me turn it over like that. We've got approximately 7 things. I don't know what the units are on this. 7 centimeters or so. So if we just number those off, and those will be our 5s, we've got 5, 10, 15, 20, 25, 30, 35. Okay. Let me take away the ruler. And I'm going to just try to be quick with this. We've got liberals here. And they're at 35. So let's go ahead and drop this down. We've got moderates next. They are at 36, so they're just a tad higher. Drop this down as well. And we've got conservatives last at 6. Okay. So we've got, this is hard to see at the side like this. What about there? There you go. There's your bar chart. Definitely have gaps between the bars on this one. All right. Last example here that we're going to knock out pretty quick. We've got the same contingency table we want to look at first. What percent of the class is male? Okay, well, we know that there are 192 students in the class, and looking at the marginal distribution of sex, 115 are male. So that, divide the 115 by the 192, and you get 0.59. So 59.9% of them are male. What percent of the class consider themselves conservative? Same thing, you're going to compare the 192 to the marginal distribution now of political views, and 27 are conservative. So 27 over 192 gives you 0.141, or 14.1%. What percent of the males in the class consider themselves conservative? Okay, so we're restricting our view to just the males here. And we want to look at the conservative males here. So 21, and instead of dividing through by 192, because they say what percent of the males, we're going to divide instead by the 115. We care just about what the men are up to. Divide the 21 by 115, and you get 18.3% or 0.183. Fourth thing, what percent of all students in the class are conservative males? Well, this is going to do sort of what you may have been tempted to do last example. We're going to take the 21 that has already been circled, and now we're talking about all the students. 192, divide the 21 by 192, and you get 0.109 or 10.9%. What percent of all the females are liberals? Let's see, what percent of all the females? So we're looking at this first row, and there are 35 liberal females. There are only 77 females in the class. So we're going to divide the 35 by 77 and get for E 0.45 or 45%. F, what percent of all males are liberals? Okay, so we're going back to second row again. And we're going to divide the 50 by the 115 to get 0.435. Okay, well, let me look at this last example to see if I want to make this or not. Politics and sex appear to be independent. I think I'm going to leave that for class. We'll talk about that at some point this next week and go over it then. All right, thanks for following along.